Hey people. We are on a really, really hard day of Advent of Code. Like really hard. Hard enough that I'm really not sure when I'm going to solve it. It's a multi-day problem for sure. And today is just going to be another day of trying to solve it. So let me walk you through what the issue is here, what the problem is that we're trying to solve. And to do that, let me get the old iPad screen share going again so that I can draw out everything and try to explain it as best I can, because it is a doozy. Just have to wait for the screen share to pop up. It takes a second. All right, so here's the thing. Here's the deal. The problem is that we have this network of pipes, right? So we've got like pipes and valves here. So we've got like valves A, B, and C that are all connected to each other. We've got valve D down here. That one's connected to A and C. We've got E, F, G, H all trailing off this way. And we've got I and J coming off this way. So this is the network that we've got. Now each of these valves has a certain number associated with it, a pressure that they release when they are open. And let me look up exactly what those numbers are. So let's see. A has a rate of 0, 13, 2, 20, 3, 0, 0, 22. Did I have that right? Yeah. 3, 0, 0, 22, 0, and 21. So these are the flow rates of each valve. So the idea being that if you open that valve, they start releasing that much pressure per minute. Now the trick is you have 30 minutes. Only 30 minutes of time in this problem to release as much pressure as possible. Now, the way that this works is you start here at space A. You can you have essentially 30 turns here. You can move to another valve or open a valve. Each one takes one of your 30 minutes. Once a valve is open, it releases the specified amount of pressure once per minute for the rest of the time, which means it's good to open higher value valves first, but only if you can get there soon enough to make it worth it. That's what makes this a sort of computationally tricky optimization problem. And that's what makes it really hard to do in dreams. So, am I dropping frames here? OBS was blipping for a second, but I think I'm probably fine. So, the path that they give me as an example that is like the fastest way to do it is like, first you go to D, and then you open D up, and then you go around to B, and then you open that up, and then you like chase all the way over to J and open that up. Then you like chase back to E. I think then you like chase all the way back over to H and open that, and then maybe you chase back to E and open that, or something. Like, it's convoluted. It's not clear that that's the best option, as is usually the case in an optimization problem. And the only way that I've figured out to actually solve this optimization problem is to think of it this way. Basically, excluding valves that have a flow rate of 0, you'll never open those. They're really irrelevant to the problem. So excluding those, what you're basically left with is a list of valves you could potentially open. Those valves are B, D, or no, C, I guess, is technically on the list. B, C, D, E, F and G are both 0, so we ignore them. H, I is 0, and J. So we have 6 things that we could open at different times in this problem, right? Like, if we, depending on the order we open these, we'll get different results. So, for example, since we start at A, if we did B first, we would spend 1 minute going to B, then open B, and then B does now 28 times 13 pressure relief for the rest of the time. Then we could go to C, now we're 27 minutes. Open C, 26 minutes. And then that would be 26 times 2, releasing 2 pressure for the remaining 26 minutes. Then we could go to D, 25 minutes, 24 minutes. 24 times 20. Then we could go to E, 23 minutes, 22 minutes. Releasing that much pressure. Then we could go to H. We're at 22 right now, right? So 21, 22, 20, kind of the wrong way. 21, 20, 19, 18. So that would get us 18 times 22, and now we have the really gnarly trek back to J, where we're at 18, but then we have to go 17, 16, 15, 14, 13, 12, 11, 10, and we would only get 10 times 21 flow out of J. So presumably then this is not the fastest way to do it. You've kind of squandered one of your best valves by going to H and then to J late on in the problem, and so you're really not getting the most of that. But you can maybe see from the way that this is framed that you can essentially just treat this. One way you could solve this is the way that I know how to solve it. I don't like it, but it is a way to solve it, is you can essentially take all the permutations of this string. That's the order you would visit all these valves. All permutations are valid, right? They, in the sense that they're a way you could approach the problem. I mean, theoretically, you could be visiting all the 0 valves too, but there's no reason to include them in the problem, so you can trim out a lot of the problem that way. But essentially what this means is there are 6 factorial possible cases to check in order to figure out what the optimal solution is, right? That's a way of listing every case. Now, typically with optimization problems, I mean, you don't want to have to list every case, right? I was looking at the knapsack problem yesterday, which is a famous sort of minimal computer science problem where you have like a backpack. You know, you've got the backpack straps there, right? Looks exactly like a backpack. There, now it's a knapsack. You've got a knapsack, right, with some fixed capacity that you can put in it. So, you know, say that maybe it can take up to 6 weight units. That's as much as you can carry. And then you have different items that have different weights and values. So this object maybe weighs only 1 unit and costs, has $2 in value. And then this one's bigger, 2 weight but $3 in value. Now you've got, even bigger ones that are like, up to potentially much larger items with greater value. But the question is, what's the optimal choice of items if you want to maximize the value that you carry given that weight constraint? This is a small example. You could easily brute force this by just picking items, but there are cleverer ways to solve this for, arbitrary sets of items. One way that you can do it is a technique called dynamic programming, which I went through yesterday, refreshing my memory on it. It relies on the fact that you can sort of do you can sort of recursively do like smaller and smaller versions of the problem, which allows you to actually then work up from the bottom, sort of like building up a table of results and allowing you to save a lot of redundant recursive work that way. Because like the key insight here, for example, is that like if I were to choose first this item right here that has a weight of 2, then I would have that item worth 2 in my knapsack. This is now down to 4, and you can essentially treat this as solving a smaller knapsack problem, where you're like, okay, now my knapsack has a capacity of 4, and how many items can I fit? What's the most value that I can fit into a knapsack of size 4? And this sort of recursive breakdown where you like shrink down the problem is what allows you to do these clever dynamic programming things. Like you can find a smaller previous problem inside your larger current problem. Unfortunately, that seems to not be the case at all here, because the order that you take these valves in changes the value that you get out of visiting the next valve. So I don't know of any way to speed this up except to just suck it up and check all of these 6 factorial cases, which, if you weren't aware, is too many cases. I mean, it's not too many. 6 factorial is actually not very big, but it's 720. 720 permutations here. I don't like it. It's not good. Now, you could... So I guess, like, the question is, if this is the only way I know how to solve it, and I was chatting with some of my coworkers today who were going through this. None of them had any ideas. They sort of shared my suspicion that this was not really amenable to dynamic programming because, like, it's just, like, there's just not that much, like, that you can find sort of in common. Like, you can't break it down recursively. Now there are 50 valves in the actual advent of code input, but as I look at it now, most of them are 0. So they really may be just angling for you to, like, recognize that and tamp it down with a much smaller thing. Because, for example, I can actually see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's only 13 things. And 13 factorial is, like, maybe within the realm of computers. Yeah, I mean, okay. 13 factorial is 6 billion options, which, to be honest, not that much. You know, that'll maybe, like, depending on the optimization of your algorithm, take you, like, up to several minutes, but probably not that bad, especially if you make a couple other cute little optimizations first. So it really may be that they're not looking for anything that computationally clever and just banking on the fact that, like, hey, computers are actually fast enough that 6 billion, that brute forcing 6 billion cases is actually not unreasonable. Like, you'll get an answer in a pretty reasonable amount of time. Unfortunately, I'm doing this in dreams. I don't have that kind of time. Like I would, my PlayStation would be running until March. So it's not happening, right? I need a better solution. Now, granted, I'm only dealing with 720 cases. That's still a lot, though. Like a lot. So I'm either going to have to like super optimize the Dreams code for speed, which is a terrifying prospect, or I need to, or I need to come up with some other clever optimizations that can allow me to skip several searches early, like bail early and stop a lot of computation, right? Because I guess here's the thing. I could let's see. There's one other optimization idea that I have in mind, which is basically that like a lot of options are going to be demonstrably worse like right away. And you could maybe just stop early once it becomes clear that this is the case. Like, I'm not entirely sure, because I think it's a little bit tricky, but basically like each valve has kind of an expected value at each step of the way. Let me delete a bunch of these arrows and clean up my visualization here. Because the thing is, like in this problem, right, if you, so if you start out at A, then the amount of pressure you expect to relieve from each valve is basically like the time to move there. It's your current time minus the time to move there minus 1 for the time to open the valve. Then that remaining quantity times this pressure relief. So starting at A with 30, you would have, 30 minus 1 to move there minus 1 to open the valve times 13 is your expected rate from B. That's the expected amount of pressure. Well, it's not the expected amount. That's the amount of pressure you will relieve total by moving to B and opening it. You can compute that for all of... There's really no reason to, actually, now that I'm thinking about it. I was thinking we would need to do that because I was looking for dynamic programming types of solutions, right? Because I was thinking, okay, we need to get a list of all the values that you could relieve. So then, C would be 30 minus 2 to move there minus 1 to open it times 2. And D would be 30 minus 1 to move there minus 1 to open it times 20. H would be 30 minus, if we were to go straight from A to H and open it first thing we did in the problem, that would be 30 minus 1 to, 1, 2, 3, 4, 5 to get there minus 1 to open it times 22. And you could math these out and see what these all are, but get out, no, iPad. But there's really no reason to, now that I think about it. I just don't think there's actually any point, because, well, there might be, maybe, I'm not sure. So here's the deal. Let's see. You could perhaps, at a certain point in the problem, sum all these up, right? Like you've got whatever these numbers are, and you add them together, and you get some number here. And it's possible that that remaining amount would be less than a previous result you saw. Like, oh, I did a previous run of the problem and managed to relieve 1,000 gas overall. And I'm at a point where you know, maybe I've managed to relieve like 150 gas so far, and the sum of the rest of the gas I could release like at all would actually be, you know, maybe this would be like 800, right? You could release 800 more. Well, all that together sums up to just 950. And you could say, well, 950 is less than my previous run of 1,000, so I don't even need to visit the rest of these valves. That run of the problem is over. And that could potentially save you some cycles. But also, I kind of don't think that will matter that much by the time you get there. Especially if you already have a bunch of other stuff pre-computed. So one thing my coworkers were talking about, which I was thinking of doing yesterday as well while I was tired and cranky trying to figure this problem out, is one thing that doesn't change throughout the problem is the distance from each node to each other node. You can build up a table that maps this relationship out for you, right? Like, so you can do, and we'll just go with the nodes that actually have a value here. B, C, D, E, H, J versus B, C, D, E, H, J. Zeros along the diagonal because you are there. And then like B is one away from C. C is one away from D. D is, or I screwed that up. D is one away from C. D is 2 away from B. E is 3 away from B. C is 2 away from E. D is 1 away from E. E is, let's see. B is 1, 2, 3, 4, 5, 6 away from H. C is 5 away from H. The reason I'm doing this whole thing is because I need to write Dreams code that will do this. And I need to actually like verify my results against something that I've done by hand. D is 4 away from H. E is 3. And then J is a whopping 1, 2, 3, 4, 5, 6, 7 away from H. J is 2, 3 away from B. It's 4 away from C. It's 3 away from D. And it's 4 away from E. Now, a couple things that may jump out to you here. First of all, there are multiple paths through this graph, right? Like, if I'm going from J to D, I can do it in 3 hops like this, you know, 1, 2, 3. Or I can do it in more. I can go 1, 2, 3, 4, 5. Obviously, I want the shorter one. There's no reason for me to do the longer. So that's a consideration to make. There's also the consideration that this whole thing is clearly mirrored along the diagonal. Like, you could see that I was filling it out diagonally as I went. I could perhaps like store only half of this, right, where I can just sort of like essentially just store this lower region of it and not bother storing like both sides, because whenever I'm doing any particular like comparison between two, I can just take the min and max of the two that I'm checking and look that up in my table. But it's probably not super important. There's probably not a lot of penalty to kind of doing both. Now, unfortunately, building up a table dynamically in Dreams, that's I'm not sure how that's gonna work, to be honest. What may make more sense, actually, is for each node to sort of store that information internally in some way. One thing that I need to do before I go anywhere, and frankly I might spend my whole night doing this, is just playing with timelines in Dreams. So I joined Mastodon the other day, because, you know, and actually somebody right away like found a thing that I shared and was commenting on it and mentioned that timelines are the secret sauce to scripting in Dreams. Timelines equals scripts is what he said. And I was like, you may be onto something. So I think I'm long overdue to learn how these freaking things work. So my understanding of timelines is that they are, I mean, obviously they play out, right? Like you can play a timeline and it'll, you know, play along. They're designed so that you can do animations and sequencing of stuff. I think that you can put like any node on a timeline and it will like power on or power off at the relevant time. So here we can see that keyframe is on at the right at the start of this. Let's see, I want to like, aha, so I can go in sort of frame by frame on this, can't I? Oh, and that's why I can move that before. Okay, so we're stepping frame by frame now, which is a thing that I hadn't really been able to do before. And so what this is happening is that like this keyframe is powering on and off. The idea of a keyframe being that it can just toggle a property of a thing in Dreams. You can drag out the length of it so that it would be on for more than just one frame, right? But it's basically just on whenever the playhead is over it. You can oh, and so this actually modulates the power as it goes along, which is interesting. I know that some nodes make use of non-Boolean power values, and I guess that's what that does. I would imagine that, for example, sound stuff probably does, but maybe that's just a general keyframe blending thing in some cases. Timelines can have multiple tracks, and I think you can put anything on them. So like this microchip is now just on for that many frames. And this is a thing that I hadn't really considered. I always thought of it as just an animation tool, right? But I mean, it is more general than that. And it is pretty wild that, and see, I didn't realize this was a thing. I didn't realize you could wire stuff up. I didn't realize that stuff that you put on a timeline had ports available. Like, it's jank as hell, apparently. Oh, I guess that's why. I guess that's why. Let's rein you back in a little bit. So, you know, I can have timers here then that like, you know, this timer I guess could still have the usual like, let's see. Yeah, so that timer ran for a second because it was powered on for a second. Because it's all being controlled by the playhead. This is fascinating because I didn't realize you could do this. Now, if I look at the properties of the timeline itself, what options do I have? Because one thing that the person on Mastodon mentioned, you can wire stuff into playhead position. No, that's not wired. You can't wire into that. Somebody was saying that you can wire into it though. Oh, you can. You can. So that put the playhead at 100%. Oh, this is dangerous. Oh, this is dangerous. So, yeah, the playhead, when you're wiring stuff up, oh man, okay. So you can actually control the playhead position this way. Okay. So this is already like, this is an important realization. Because here's the thing. I could. So I can take, for example, the I think that I can get the timeline length somehow. What is this, by the way? Ignore frame rate? Wait, what? No, I wouldn't want that most of the time. Okay. But good to know that that exists. There's a restart. I don't know if I care. There's show sidebar. Oh, that's fun. So you can like, oh no, I wish I had been doing this the whole time. I totally get what this guy is saying now. You can just sequence things this way. You know all the trouble that I've had getting things to happen in a sequence in dreams? Well, little did I know I should have just been putting them on a timeline, because then I can just be like, run this part of my logic, right? Then, like, run this part of my logic, then run this part, and I can basically just like set each of these things to be like 1 frame wide, and then it'll just be like, you know, I can essentially just have like a next frame step kind of thing where I just like have a variable wired into the playhead position that just sets like, you're on this value now, you're on this value now, you're on this value now. And furthermore, even more so, one thing that the guy was saying is, I gotta pull up Mastodon now. Once I clicked that each frame of a timeline can essentially hold an instruction, that opened all the doors for me. So you can cycle through a bunch of checks with an exit condition, or use an argument wired into the playhead to select which frame to power on. If each frame has a variable get or set, now you're reading or writing into a data frame, stuff like that. And this is like, whoa, wait a minute. Did this guy just unlock lists and addressing for me? Maybe? I'm not sure, but maybe. So here's the thing. I'm not sure that I've got ideas. All I can say is I've got ideas. The secret sauce is timelines equals scripts. And this is just like, I just need to take the time here on day 19 of that I've been doing this, day 16 of problems, and try to figure out what all you can do with what may be the most powerful feature in Dreams that I've never used. So here's what I want to try. I want to try something here. I want to set up a few elves with their own variables on them. I'm going to have microchips on each of them that just have some logic that they're doing. So let's scope into, well, let's see, let's not actually scope in. Let's just add a microchip here, and then we'll group those up. So now within here, I can just sort of add the usual, basically. Let's add a variable. It doesn't even really matter what it is. We'll just call it like beats. Beats. That's good. That's a good name. Vitelectrix vibes. And what we'll do what I'm really very curious about is this. Can I put like, can I make like a variable modifier? That's just like floating here, right? And this is going to modify beaks. And only in the here scope. It's only going to modify variables in this group. So this is my way of doing like per instance variables in Dreams, right? I make a group so that we have a here scope, and then I can make variable modifiers and stuff that only modify variables that are here. That works great. I've been using that reliably. And I'm going to set this to whatever the value is wired in, and that's the next thing. So now my question is, can I put stuff from inside other groups on timelines and have them work? That is my fundamental question. Grab the dang thing. It's really hard to... They want to be really long for reasons unclear to me. I want them to be 1 frame long. And here's what I can do. So I've moved something that belongs to this group into here. My question is basically, is the group relationship preserved despite the timeline controlling it? Because if so, then I have something very powerful on my hands. Let's start by putting this number displayer in the world. I'll scale it up, but otherwise I don't really care about how it looks. I literally just want to see the number that is stored in this variable. And what I'm going to do is set up a little bit of extra shenanigans to power on and off this timeline and that kind of thing. So I'm going to just make another microchip, upon which I can place my timeline, because I want to be able to easily power the timeline on and off, set up some sliders and stuff. I just want a little space to put this stuff. So what I'm going to do is add a variable slider, or value slider. This thing is going to go from like, sure, that doesn't matter. It really doesn't matter what value it holds. I'm just going to be changing it as I go. I'm going to have a switch here that I can use to power this thing on, like power on the entire thing at once. I'm also going to collapse this down to one track because I really only need one track to test the idea that I have in mind. We're going to make this thing pulse just because I want to basically just like, when it's running, you'll see that it just, oh, I'm done. I didn't switch it to pulse mode. There we go. So you can see now whenever I click this, it powers on for one frame. What I want to do now, I'm going to duplicate our friend the elf. Did that duplicate that? No, it didn't. This is concerning. Hold on. I have to like put this back in this group temporarily. You know what? This is stupid because I think that what I can do actually is just put nodes on the graph here that would basically like, hold on. Can I like change the meter or something? Why do they want to be so long? Just stop being so long. Stop being so long. Okay. I really don't need the like sidebar on this thing, do I? No sidebar necessary. I can wire stuff into this, right? Like I can pass that in, and now only when the playhead is on that thing will it power that node on. And that can propagate through to both the power and the value. Although I guess that's probably not exactly what I want. I probably, oh yeah, I don't need that. I just need the value to be going into each of these. And the power goes into each of these. Yeah, so there we go. That one powers on that variable modifier. I'm like actually sure that this is going to work. So let me clone this. And now you can see, you know, this guy has his own variable modifier and his own variable. I can, again, wire that in. I can duplicate this node and use it to power this one. I can do that like another time, I guess. Might as well. I'm just trying to essentially test my first array. So again, we will wire it up to the value slider. So that's the value that this variable is going to be set to. And we'll create a new node on our timeline. And that is going to power it. And this is good enough, right? I can now like shrink the timeline down to just that. So we have a grand total of three things in our timeline that can be active. None of which are active right now because the whole timeline is powered off. But now. First of all, I'm not actually sure that I can get the length of the timeline here. Like, I don't know if I have that power, but hold on. Oh, it was just being weird about how it rendered that one, but it's still only 1 frame long. Okay. So if I Because, like, what is this doing? That's like setting the in and out points, isn't it? "33%, 67%, 100%." Right. I mean, this is what I expected. It would be convenient if I could get the length of the thing out, but I can hard code it if I have to. Because what I'm essentially thinking I can do here, we'll like set this to 3, right? That's the length of the, or really I should set it to 2, right? There are 3 elves that I can address this way with indices 0, 1, 2. I can wire this into the playhead. Now, it's not perfect because I need to divide it by 3, which is where I was wondering if I could programmatically get the length of the timeline. That would be convenient. I can divide by 3 for now, just to verify this idea. So I now have programmatic control over which of these things I'm going to power on using this timeline, which means, let's run the program. Let's say that I want to store the value 55 in elf1. Pow, that worked just brilliantly well. Look how well that worked. It occurs to me that I missed a step. The the nodes have nothing wired into them, so of course they're always outputting nothing. That's great. What I basically need, actually, is a steady value that I'm powering on and off. I mean, I guess really I just need like, I just need something on the timeline that outputs a 1. Hence why I'm grabbing this switch, apparently. So let's wire that up to these power things instead. Okay. Let's trim this back down. And let's try it again. So we want to store 55 in elf1. And then we want to store 18 in elf2. And then 76 in elf1. Oh my god. This is how we can do it. We can do lists. We can write into lists. It's possible. Oh man. Oh man. Okay. All right. Okay. Okay. This is huge. This is actually huge. Oh man. Okay. 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 This is a big deal for me because here's the thing. Before, the only way that I would have had to, what I've been doing, first of all, I should say, is if we look back at any of my previous days, I've been making huge selectors and wiring out, like, I'll just have, you know, tons and tons of output stuff that is hooked up to the selector, right? So it'll be like, oh, I'll have all these, right? And then I'll have to like go through and power each of these individually, right? And then collapse them all into another node to get their output. And that's the only way that I knew to like cycle through something and power something on. But that had the problem of like I could only have up to 10. And if I wanted to go higher than 10, then I had to like add multiple levels of selector and have some modulus magic that would toggle them on and off. And that was like a huge pain. What I could have been doing the whole time, and like I cannot believe this, is I could have just been using a timeline. Because what is it but a time, like a scrubbable power selector? Like, it is a selector. It doesn't have the convenient button to step to next, but you can very easily achieve step to next. So, I mean, this is like actually pretty big for me. This is pretty big. Pretty exciting overall. So, I mean, where does this leave me then in terms of this problem? So, like, what this means is I can have actually, I could have like n different variables per node that I can sort of address using an index like this, essentially making an array, right? Where I can, because like, I should be able to just like, you know, I can set this, oh, I need to shrink this back down again. Because like, I can just use this to select which index I want, and then bam, set or get a value, pow. Pow. Yeah, this is huge. This is actually huge. There's a lot I can do with this. Yeah. Okay, so let's, with that in mind, man, there's one thing that I really would love to get, and I don't know if I can. And that is the timeline length. I can wire into the playhead. I can wire into stuff on the timeline. But I can't seem to get the actual number of frames or the time in any way. So I'll just have to hard code that. But that's fine. I'll deal. It's not that big a deal. So let's start up a new creation here. And think about how to do part one of this problem. Part one of this problem is essentially to figure out the distance to each of these nodes. So the situation, to back up and look at the iPad again, I see the screen share has unfortunately stopped. Let me get that going again. Just one moment. There. So the situation I have is that I need to, first of all, I need to like put all of these nodes in the scene somehow. You know, they just need to be like existing in the world in some way and like connected to each other or telling each other about each other in some ways. Excuse me. And then I need to be able to sort of traverse the graph. I need to like seek out the shortest path to each and every other node. Now, what that means in my case, I think, is say that I was at D and I wanted to find the shortest path to J. I think what I would do probably is, I've got so many options now that I can theoretically use arrays. So many options. There's one other thing that I need to play with. But basically, what I think I would do is see that I have 3 ways out of this node. You know, I can go this way, or this way, or this way. And essentially like emit 3 seekers that would go that way and report if they are, essentially track if they are the thing we want. And then if not, because they haven't found J yet, then like this one would go probably down this and this and this, but this one would die because it found a node we had already seen. This node would be marked as new but not finished, this node, you know, and then it would like, each of these would be sort of like recursively like spawning a bunch of other little seeker things that fan out across the graph. All of those little seeker gizmos, I would hope, would be sort of wired back to the D node, whatever it is, so that when they get there and find the node that they were looking for, they can be like, I moved this many steps, and just send that value back across the wire. First one to get there wins, all the others get fizzled, and then it repeats the process for the next thing. So a recursive flood fill of this graph again, which like is complicated, and it'll take me all night to do if I even finish it tonight, because I started extremely late. Started at 10 p.m. So I kind of wanted to do at least just a short stream tonight to look into timelines, learn how they work, keep pondering the problem. As it is, realistically, my last week of advent of dreams here, and I think this problem might take me all week. It's a really difficult problem. It's a straight up optimization problem with multiple stages and including recursion. It's like about as computationally difficult as I might ever be able to achieve in dreams, and a worthy opponent to spend the remaining week on. That's kind of what I'm expecting for this. So I'm not going to be up super late trying to beat this tonight, but what I will try to do tonight is get part of this recursive flood fill sort of thing going, because as part of my overall problem strategy, I need it to be the case that each node knows how far away all the other nodes are. That's an important part of... Is that an important part of the search strategy? Wait a minute. Is that actually important? I think it is, because that's what I use to actually compute. Well, wait a minute. Do I need that? Because I was going to be doing this more simulationally. The place where knowing the distances ahead of time would come in is if you wanted to kind of speed up the raw computation at each step of the way, where because you know it's this far away and it'll be running for this many things, you can just compute the total amount of pressure relieved by that valve immediately. But I'm not probably going to do that, because I'm probably going to be actually simulating this. So we might not actually need to compute those distances. What we might need instead is to know how to traverse the graph, right? How do we actually get to our destination? If we're going to have like a little agent sort of running around this system, right? If we have our little guy running around this whole thing, right? Starting at A, and then running to D and opening D, and then running up to B and opening B, and then running down to J and opening J, and then running down to D, all the way to H and opening H, and then running back and opening E, and then opening C. You know, if that's like the whole, if we want to see that happening, and I do, because that'll be fun, then I need to actually I need it to be the case that if my sequence is D, J, H, E, C, or whatever, D, B, J, H, E, C, and I'm at A, or really any particular point here, I need to know, like, if I'm at D and I want to go to B, I need to know what path to go to get there. If I'm at B and I need to go to J, I need to know what's the shortest path to get there. Thank you, Coding Vibe. Do note, it's not executed in Dreams yet. But I hope to get there. So that is, so really, as I see it, and this is why I'm going to spend days on this problem, there's several components to actually solving this problem. And let me generally break them down. We have step 1. Compute all permutations. I'm sorry, iPad, what are you? Can I not scroll down to my own drawing anymore? Cool. As I was saying, compute all permutations, because the sort of string here represents the order in which we visit all the valves, and we're going to just check all 720 permutations, and I'll find ways of doing that concurrently in Dreams to make, to at least like significantly shrink the amount of time spent on it. I had the idea earlier of having sort of like a fixed pool of workers, and then like they all have like tags that are on and off for when they're like ready to receive another job or whatever. And so then, you know, you could have it that like as soon as one's ready, then like the next permutation gets dispatched, and then the like parent iterates to the next, and they can like farm out jobs as they all finish. So I might be able to speed it up that way, but that's a later step, right? So step 1, I'm getting ahead of myself again. Compute all permutations, or just simply be able to iterate through all permutations. I guess that's what I'll say. Iterate through all permutations. Iterate through all permutations. Step 2 is find the shortest path paths from node to node. Because basically this is like, you know, if I'm going to have this whole graph represented here, every node in my simulation needs to just know if I'm going to J, I go this way. However that looks, I'm really frankly not sure how that looks. It might take a bunch of manual setup. I think that would actually be relatively appropriate. To essentially just have like some manual wiring between things, because like I think that's a reasonable compromise. That would also allow me to set up a pretty cool like visual pipe system on the ground that like, oh, imagine if I had like a bunch of like factory floors, each of which have this sort of layout on them, right? So then I've just got like a bunch of floors with the elves running around, all sort of working on their own parallel copy, and I can just, as factory supervisor, like fly up and down between the floors to see how they're all doing. That's probably what I'll do for the visualization. But each of the nodes in my graph needs to have information about which way do you go to get to other node. And then we need to like have one elf perform one permutation. And then, because we're definitely not going to wait for 720 things to run sequentially, run jobs in parallel. So I have to make some kind of like parallel work dispatching. I mean, basically a thread pool in Dreams. So this is my path through this whole thing. Now, 1 and 2 are arguably interchangeable in that I could really do either one first before I do 3, but which one do I feel like doing tonight? The permutations thing is kind of interesting purely logically. The shortest path thing is a gnarly recursive thing that I probably don't have time to do tonight. So I guess iterate through all permutations it is. But I got a plan now, I guess. So this, I have to like send this to myself somehow. Do the old message myself on Discord trick. Okay. So let's figure out how to iterate through permutations in Dreams. I probably shouldn't have put the iPad away because I think I have more to do. iPad, thank you. Okay, we're still alive. So if I have, A, B, C, D, E, and I want to iterate through all these, what's an actually nice way to do that? I mean, essentially I think of it sort of like choosing, really I just need to figure out an iteration order and then sort of figure out how to represent that. I'm not sure that it matters much. I mean, obviously it should be predictable, but I sometimes think about like I'm sort of moving the E through it, but I'm not sure that this makes sense because maybe now the next reasonable thing would be to swap those around, right? And then maybe no, here's a more reasonable way to do this. Say that we start with, essentially I'm thinking we have like 5 slots to fill, right? And we're just going to sort of for each on each of them, right? Where it's like we're going to start with A, right? And then we're going to start with, well, we can't do A because that's already been taken. So we would start with B, and then C, and then D, and then E, right? But then the next choice would be, if we were sort of for eaching through this, is like, oh, maybe this would actually achieve the same thing that I was just doing. If we were to sort of do this recursively, we had 2 choices. Well, let's see, we had 5 choices here, 4 choices here, 3 choices here, 2 here, 1 here. We've exhausted our 1 choice at this place, so now we would step back to this place. So then it would be like A, B, C, E, and then D. And now we've exhausted these two choices, so we would move up to here, right? And so then that would be A, B, D, C, E, A, B, D, E, C, A, B, E. Yeah. This is a pattern that I am okay with. And now that we've exhausted all three of these options, we would step up to a C, B, D, E, and so on. So you can kind of see how that process would flow. Now, what's a nice way to iteratively go through all that? Is there some like numeric representation counting trick that I can do, you know, where it's like, you know, oh, it's 1, 2, 3, 4, 5, and then 1, 2, 3, 5, 4. I mean, this is clearly not helping. I was thinking before that it would be like a binary sort of thing, maybe. Like that would be the magic that you do if you just want to like iterate easily through it. But doesn't seem to work very well. I guess for what I'm doing, it would not actually be that bad to just have like 6 for loops. It's not pretty, but 6 counters all wired into each other. It would work, right? Right? I mean, like, that's all I need. I just need something that works. So let's get in on this. Get ourselves some room to work with. And pull out some counters. I'm not gonna use my iterator thing for now because I think it's gonna be painful enough with just what's, I don't think I need all that extra pain basically. So this is what I'm dealing with. You know, 6 counters, each of which goes from, I guess we'll say 0 through 5. 0, 1, 2, 3, 4, 5, right? 6 options. And I can step to increase the count, then this basically does let me let's see, maybe what I want to do is actually have them all go up 1 higher because I want to use the counter full signal to do some shenanigans. I want, when this thing is done, when the counter is full, I want this to reset and increment the counter above it, right? Because what that lets me do is like, you see, I've done like a like sort of a number, I mean, sort of like a speedometer, right? Where like 1 fills up, it rolls over the next digit. 1 fills up, it rolls over the next digit, and so on. Which I think I could basically use to my advantage here. The difference being, I guess, that I need to skip a bunch of options that repeat values, which is like scary. That's the weird bit. That's just the weird bit about it. Skipping things in this iteration is just strange, because I guess, you know, for two of these it might be okay. Like, if the count progress of this, I mean, we could use count progress in place of counter value. It doesn't really matter. You know, if this equals this, then we should step this one as well, because that one was a repeat. Now this doesn't work because of how pulsing works, but I could sort that out, because this should have incremented one more up to, oh right. Freaking annoying. How do I make it so that the number of things coming in here increments the counter by some amount? That seems like what I want to do. I don't like it, but that seems like what I would actually want to do. Sort of feel like what would it be? It's like when I press this, I want it to increment, and then I want it to like keep incrementing until these are not equal anymore. So in order to get like a proper test here, I need to OR these together. So if it's equal to any of the previous digits. Why is this powered? Because they're equal. Yeah. So that would like immediately step it, which is what you'd expect. But on each power on, I need it to, let's see here. I sort of need like an overall gate on this thing where like, I think that this will power us into that state. Let's see. I need something sticky here. That's the thing. I basically need to like go into some state that's going to be like powering on and off and cycling the counters until we get to the next thing. So if we're in this state, maybe this should actually be this one instead. So we will be like advancing no counters, then we toggle into this state, and it will, it has to start like, I guess rapidly pulsing, or I could just like run a short timer. Let me see here. We'll make it kind of short for now, but So if these things, when we toggle this on, we're going to step to the next thing. This logic is jank. One time only, we're going to step to the next thing. And then, while we're in that state, we're going to be running this pulsar thing that takes us to the next state for as long as it's a duplicate of some previous thing. And as soon as that becomes false, that's going to toggle us into state A. So let's see if this works. So that ticked it up to 1. Great, it didn't work. Because this thing didn't actually pulse on. I really wish pulses just weren't like this, you know? Does this work? If I just power on and off random things, does this work? Hey, that actually worked. So it advanced past the 1-1 case. Except it was supposed to do more than that. Let's see. This case was supposed to... Dang. So what happened here is that this thing filled up, and then 1 frame later it did the reset and the click up to the next thing. And because we had our one moment where this was on, it oh dear. For crying out loud. Yeah, that didn't work because it just pulsed on a port that was already hot. Okay, so I need to... This is the most annoying part about dreams, man. How do I do this? The basic rollover mechanics seem nice. I probably shouldn't be powering this way because this should probably be running yonder timer now. Yeah. Oh yeah, that actually just works. Okay, so having that be powered was a mistake. Because here's the thing now. What it's doing is doing what I wanted and skipping whenever this is equal to this or this, it's like skipping 1 ahead. Yep. So, what does this mean for me? I can also make some OR gates that represent the next stage of the chain, right? Like this one equals this one. And wire that into this OR as well. The wiring's messy, but I'll figure that out later. So this now actually iterates through until all three are different, which is pretty sweet, actually. So like, now it like skips ahead to there, and this is the first point at which, let's see here. I'm confused by the flickering in this part. I was hoping to use the like output of the selector as an indicator of whether things are okay to use. But the fact that we are like flickering onto A at all is strange. Like, what got us here? Probably the stupid power on the NOT gate, but I'll figure that out later, because for the time being, the core logic is actually working just like how I wanted. Essentially, it'll go through every single permutation with repetition and skip the repetitions. Yeah, that's pretty sweet. Yeah, it skipped all of those because these two were equal. Yeah, this is cool and all, but what I can also do, you know, if I were to actually extend this up correctly to have like all of the checks at every step of the way, you know, where this also now like would check against. Oh, this was not the correct one. Yeah. You know, if I wire all of these together, oh, what did I mess up? Ah, I needed this one. Haha. For this. So now it's actually got to roll through several ticks up to there, where now these are all different yet again. That's really nice. I am a fan of how it just automatically skips all of these incorrect permutations. It's just rolling over until they're all unique again. That's quite pleasant. So now I just need to deal with the flickering that I'm occasionally seeing on this. Or maybe there's another sign that I can go through. Oh, really though? It's just the output of this OR gate. That's the only thing that matters. Yeah, what am I thinking? As long as this is true, don't use the value because there are duplicates. I mean, that's literally the thing I'm observing. As soon as that goes false, that's it, right? I mean, now it's good to use. Anything else can happen on this end, but it purely just goes on and off. No weird flickers, no shenanigans. Okay, there was a shenanigan there. I regret to inform you that there were shenanigans. So like it's just on and it stays on until I touch it. That's the hope. It'll take some time, but nope, that flicker. What was that? What was that? That's my problem. When did that happen? What caused that flicker? That flicker at the end is very strange. What actually causes that? It seems like it happens when the bottom one rolls around again. Under some circumstances. Maybe? So what causes it? It's only like the final wraparound. Oh, I know what causes it. For one tick, this thing is at the maximum value of 6. But so it's the frame before this one ticks up to 2 and this ticks down to 0, which are both triggered by this counter being full. So it's that counter being full on the frame where, okay, that's frustrating. What do I do about that? Part of me thinks that maybe doing this with counters isn't a good idea, but part of me is also like, hello, what else are you going to use? Now, the other thing I would use, to be clear, is like a base 5 number, basically, which I could achieve with some modulus trickery. Where it just continuously increments. And I kind of split it into places and The problem as I see it is this. You know what? I say screw it. I'm not gonna figure out how to solve this robustly. I'm gonna put a damn timer on it. That's what I'm gonna do. I'm gonna put a freaking timer on it. I'm gonna like require the signal to be hot for a certain amount of time before it goes anywhere. And you'll like it. I'll need to like, in fact, I mean, it could be basically as straightforward as just like, wait for this to ramp up and wait for it to equal 1. Or really wait for it to ramp down. And wait for this to equal 0. Throw a node on there just so that it's visible. So now I've literally just debounced it. Yep, there we go. Perfecto. Beautiful. And actually, I could replace this with a horrible, 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 bad, terrible thing. For maximum rate pulses, you just can't do better than the NOT gate wired into itself. Do not stare directly at the hyperpulsar. I contained it in a microchip so that you can't see it. Now, where the heck does this even wire into? Right, this increments the counter. And what else does it do? Oh, it resets itself. Well, that's lame. Nobody likes that. There, so that's ticking as fast as it is possible to tick. And this just don't go on until the smoothinator smoothinates it. That's pretty nice. Yeah, I like it. Okay. Okay. This can work. Do I need to power that on? Yes, because this... Well, actually, why? Because we're already in this state and never got kicked back to that state. So, it's ugly, but it obviously works, so who am I to question it? What this means for me is I can now consolidate all of this into a sort of permutator. Permuter would probably be the right word, but I like permutator better. So this is going to be my permutator. This thing is going to be replaced, or I guess just sort of kept alongside an actual node for next. We'll just wire into that because it is convenient. Okay, to be clear again, this didn't go during that flicker. Nope, because it was just one frame jank. Now, the rest of this jank, I really desperately need to find a way to untangle somewhat. This is awful. I'm sorry, Homestar Runner isms are slipping through again, as they always do. So this thing, when we get into this state, you know, it ticks to the next one, and then it'll, at that point, start the super frickin' pulsinator, which you dare not look at. Pulsinator. Okay, and then I just have to wire up the rest of this horrible, horrible cascade. Now, I don't think there's any benefit to having them staggered the way they were. And I kind of just want to redo all of this wiring. So I'll keep this as a reference. I need that as a reference. That's sort of close enough to keep the wires relatively visually clear. I mean, it's terrible, but it is relatively clear. And then I can set up all the equalses, which are all terrible, you know? They're just all bad, but it's not really the end of the world. I think I am going to try and do them in stages, sort of like I had them before. And probably what will make sense is, let's see here. I need 4 of you, or 6, I mean, I need 6 of you total. I don't know why I said 4. That was not correct by any means of counting. Wire into any of these. I don't think that I can use a wide calculator to help me at all here, which is why I'm bothering to do this mess. So this is basically if this one is equal to any of these other digits. So there's that one. That might be worth shoving in a microchip, if we're being honest. It's terrible. It's the worst. But it's because of all the bees. Not the bees. I need an input node for the bees. I do know what it's like, son. I do. I kind of love this like super fast-paced electronic music. I don't know why. All right, so there's one digit. Now the rest are easy-ish because I just delete one. And shove everything up to compensate. I still have to wire them all in, but that's fine. Because this is going to be... Wait. I'm sorry, hold on. What? Wait a minute. One of these is wired twice. This one. What are you doing, man? Like, come on. Come on, you're wired twice? Unacceptable. I was like, I definitely don't need 6 comparisons between 6 things. There's only 5 possible... If I'm starting with thing A, and I want to pair it with 5 other things, I need 5 equal signs. One was completely redundant, and I didn't even notice. That's hilarious. I love it. The song really thinks I don't know what it's like. Okay, now we can duplicate this up. It's still a little bit short on outputs and stuff, but I can now just delete one and we'll be in the correct situation. Oh, I gotta open it up and wire up. This one now comes into here. This goes into here, this to here, this to here, this to there. That seems right. Same deal. Delete one. Scootinate. Shrinkinate. Wire this one up to that port, and then wire all the ones above it to the equal signs. And shrink that just so that it knows its place. This one against this and this. And one more. Don't even need the OR gate anymore. We just have this for visual parity. Because now, you see, I can OR all of these together, and it will be beautiful. This is terrifying, but I kind of like it. Can I like scoop up other wires with this? No, only if I do. Well, I could actually do some scoopage like this. Which might help. I'm not persuaded it will help. Making them all a little bit straighter is probably actually good for visual clarity, so. Yeah, those other wires are just some spurious stuff coming out of here, which I should really move out of the way. Is that better? Have I created an improvement? Sure. It doesn't really matter. Hi, Buttered Penny. Yeah, this is actually kind of the most spider webby wiring I may have ever done in Dreams, which is saying something. That sure does say something. Well, I'll leave that because who cares? At this point, I need to wire up kind of the remaining output of this, like that. This powers this, and this powers this. What else is this wired up to? This thing currently sends you into state. Why would you need to worry about sending into state B? I'm gonna experiment without that wire for now, but I am going to power that. Does this get to the desired end state? Where none of these things are equal. This should basically be 0, 1, 2, 3, 4, 5. Which takes some time because it has to wrap several of these all the way around. Crazy to think this is happening literally as fast as possible, if you can believe it, because this thing over here is pulsing literally as fast as the game will allow. This is as fast as I can send pulses in on this. So, sort of annoying that it has to do this. I suppose I could make my job easier by starting each counter. I could just start in the desired start state, But, and in fact, I think I'm going to, because this is actually a royal pain. So we will start the counters at 0, 1, 2, 3, 4, 5. At which point we're good, but then when I tick to the next, yep, it wrapped around. The objective is for none of these to equal each other. That's why the spider web. And basically, whenever I flip this switch, I want it to like automatically roll to the next case where none of these counters are the same. They're all mutually unique. Is that correct? Is there any need for this selector at all? I don't think there is. So let's reset back to the original state. When I pulse that, it rolls around to 0, 1, 10. I should really like put some previews. As it is, yeah, you know what? I'll wire up some outputs here. And on these output nodes, I will also put value sliders of appropriately large range, just as visualizers of the numbers that we're outputting. And the, oh, phooey, this is going to be annoying. Each of these I have to pull the current count out of the tweak menu. Oh, it doesn't change the layout. I'm saved. Because the node was already tall enough. So it's 0, 1, 2, 3, 4, 5 right now. Then when we run again, it jumps up to 0, 1, 2, 3, 5, 4. And then up to 0, 1, 2, 4, 3, 5. 0, 1, 2, 4, 5, 3. 0, 1, 2, 5, 3, 4. This is good. This is good. 0, 1, 2, 5, 4, 3. So it's going through every permutation of the numbers 0 through 5. Now this one takes a while, apparently. Had to roll around to something. 0, 1, 3, 2, 4, 5. 0, 1, 3, 2, 5, 4. 0, 1, 3, 4, 2, 5. This is great. And the logic has ended up expressed a lot more simply and less statefully now as a result, which I am pleased with. Let me, in fact, shrink some of this stuff closer together because there's really no reason for this to be so big anymore. Lots of output nodes. I guess that's why it's so tall. This Pulsey boy is probably best placed over here because it is simply another thing pulsing the, like, ticking this thing up. And I can much more reasonably route wires like so to communicate this fact. And that is just my smoothed output. So that probably doesn't need to be anything more than just that. Although, maybe I will just, you know, line those up all pretty like. It's kind of unpleasant how all these wires are overlapping the, well, you know what? I feel like, oh no, hold on. Let me make this a little prettier first. Very important, obviously. I gotta line these all up good now. Must make wires line up good. Because what I can do now, you see, is route these completely uselessly up and over. This will be the most beautiful wiring ever achieved in Dreams. This program is going to be sort of my Dreams magnum opus. I don't think that I'm ever going to do something more computationally difficult than this, like ever. So, kind of feeling like going out with a bang and making it just look really freaking good. I should really probably move these closer in now because they're uselessly far away. This is so deeply unnecessary. But also deeply satisfying. Beautiful. Have you ever seen a more beautiful microchip in your life? Doing exactly what it needs to do. And I think this expresses the logic really clearly. Because the thing is here, what this does is you power this and it ticks the counter to the next value. But then as long as any of these digits are equal, it keeps the pulsinator on and just keeps increasing the counter value until all the digits are unique again, and that's it. We then, because of some slight jank, have this signal manipulator here that essentially just debounces things. You can see that it sometimes flickers off and on, but what's a little flicker, you know? Works great. Works like a charm. Need to name all these nodes, I guess. We'll just call it U's. The rest can all just stay as they are. This is our permutator. And with that, step 1 of our problem is complete. Step 1 of many, but let me pull up Let's View just so that I can have the satisfaction of checking it off and then quitting my stream for the evening. So of these 4 major steps, iterate through all the permutations of the valve orders, find the shortest paths from node to node, have one elf perform one permutation, and then run multiple of that in parallel to make sure that it can finish before the universe ends. We have now done step 1. Iterate through all the permutations. We've done that, and I feel good about it. So, with that, I'm going to call it for the evening. Thanks for hanging out. I appreciate it. I will not be streaming tomorrow night. It is first robotics night for me. But after that, on Wednesday, I should be back again. And I can hopefully do part 2. And then, who knows? Maybe Thursday, part 3. Friday, part 4. I mean, by the end of the week, which, you know, is Christmas Eve, hopefully I have this done. I think this problem is going to take me the rest of the week, though, at the rate that this is going, where I have to just do difficult stuff. 2 hours on this, so serious business. But yeah, I will see you next time. Bye.